Hello and welcome. I'm Christine Perey, and I'm chairing and hosting today's Research Committee webinar. Welcome, and I think we can have a very, very exciting talk about a body of work that's really evolved over, I don't know how long it's been, 4 or 5 years. Christoph Ebner with us today and his colleagues around the world. I've been working on multifocal vari-length display technologies to overcome vergence problems in displays. So I'd like to invite you all to stay with us and enjoy this exciting presentation by Christoph. Anytime you have any questions, please put those into the chat interface of your BrightTalk field, your page. This meeting will be recorded and available using the BrightTalk platform and, of course, on YouTube after 30 days. So I think this is a good place to start, to transition. Turn it over to you, Christoph. Please introduce yourself and share with us all the work that you've been doing. Congratulations on your thesis defense, and welcome. We look forward to your talk.
Thank you, Christine. All right, so I will just quickly share my screen and bring up the presentation. All right, so hopefully you can see it. I also want to welcome you all and thank you for attending this webinar, this talk on dynamic multi-layer mixed reality displays. Quickly to introduce myself, I'm Christoph Ebner, a postdoc at Graz University of Technology in Austria, and I'm working on designing and building head-mounted displays with the goal in mind to test and evaluate novel concepts which hopefully improve user comfort. I've also put my contact details in the announcement section. So if you have any further questions that come up after this webinar, just feel free to contact me. Okay, thanks for the introduction. And to kick off this presentation, I want to briefly talk about the ultimate display and also what it takes to build such an ultimate display. And of course, any conversation on this topic would be kind of incomplete without mentioning the pioneering work of Ian Sutherland and his Sword of Damocles head-mounted display, which to my knowledge was the first augmented reality headset. And you can see this in this picture here. But this was back in 1965, so a long time ago. And nowadays, our head-mounted displays, they look more like this. So the question is, how close are we to building an ultimate display, and also what constitutes an ultimate display? And to answer this question, Douglas Landman from Meta Reality Labs coined this term visual Turing test, which he describes as the end goal of providing a VR or AR experience in which the virtual content is visually indistinguishable from the real world. So essentially, once we solve these tests, we know that we built the ultimate display, at least in terms of the visual experience. And so for us researchers interested in visual perception, the question has now shifted towards how close are we to solving this visual Turing test. And to answer this question, if you think about the human visual system, we can come up or derive several requirements of display parameters that might quantify how close we are towards solving this test. So for example, parameters could be resolution, field of view, dynamic range, color gamut, and so forth. And here on the right side, you can see the requirements for these individual parameters. And actually, for some parameters, we are pretty close. And on others, we are quite far from reaching the limit of the visual system. But there is one parameter that kind of stands out to me, and that is depth cues. And depth cues essentially are hints to the brain on how far certain objects are away from you. So why are depth cues so important? If you think about it, even if you don't get resolution or field of view dialed into 100%, users can still have a nice mixed reality experience. Or, for example, if the dynamic range of the display does not cover the entire perceivable range, it's usually not that big of a deal. However, depth cues are different. So if you fail to provide proper depth cues, users really can get sick from using the HMD. And in fact, modern HMDs provide almost all depth cues except one, which is focus or accommodation. And that leads to the so-called vergence-accommodation conflict, which in turn leads to all sorts of problems, including eye strain and even nausea. And to solve this problem was actually the driving factor for my research. So in order to understand what the vergence-accommodation conflict actually is, we need to first understand vergence and accommodation themselves, and also their interactions, how they're linked. So vergence essentially is the rotation of the eyes depending on the depth of the object. So in this little example here, the user looks at the dog, but when the gaze shifts towards the cat, which is closer, the eyes rotate inwards. And the state of the muscle which control this movement essentially serve as a depth cue for the brain to tell the brain how close the cat essentially is. And accommodation, on the other hand, is the focus adjustment of the lens in the eye to view the object clearly. So similar to an autofocus of a camera, the focus distance of the lens in the eye changes. So the object we are looking at is in focus. And in this example, we perceive the cat in focus and the dog is kind of blurred out. But if we once again switch the gaze to the dog, now the dog is kind of in focus and the cat appears blurry. And what's important here, and this is important for the whole talk and the whole vergence-accommodation conflict, is that vergence and accommodation, they are coupled. So throughout our childhood, we essentially learn to automatically focus on the objects we are verging at. So now let's look what happens in HMDs. So here we usually have a single image plane at which all the content of the scene is rendered. So both the cat and the dog are shown on this single image plane. And for the sake of this example, let's assume that the image plane coincides with the focus plane. And in this case, you can already see the difference to the real world because both the cat and the dog appear in focus, which is kind of incorrect. However, it actually gets worse once the user looks at a different object, at a different depth. Because accommodation essentially follows the vergence, both objects appear blurred out, and the contrast of the scene is severely reduced because, once again, both objects are actually shown on the single plane that we are now not focusing at. And that's what's causing eye strain and nausea. So to summarize, commercial headsets currently usually have a single fixed focus plane at a far distance. And consequently, close objects appear blurry. And in fact, the vergence-accommodation conflict is most severe within arm's length. But if you think about it, most interactions, such as working with machines or performing medical tasks, for example, happen within this range. And you can see this problem once again here in this example. So the user focuses on this oil gauge, but since the augmentations are both shown on a single image plane at a far distance, both AR labels appear blurry. And that's what's causing the aforementioned problems. So in order to make working with HMDs, for example, in workplaces viable, we really need to solve this problem. And of course, there have been some attempts in the past to achieve this. So I will just give a quick overview. And roughly here we can distinguish between 4 different display categories. So first, we have varifocal displays. Instead of having a static image plane in varifocal displays, we measure the current vergence distance of the user with an eye tracker, and we shift the image plane towards the measured distance. So basically, we have some kind of system which allows to shift the image plane dynamically. So for example, this paper here by Pat Manapan and colleagues, they use a motor to shift the image plane. So they measure the vergence distance, and then the image plane is shifted towards the measured distance. And essentially that means that the image plane is always at the depth that we are looking at. Of course, the downside of varifocal displays is that they rely on precise eye tracking. They also, since we still have a single image plane in varifocal displays, they still do not provide fully accurate focus cues because all content is still shown on this single image plane. Next, there are multifocal displays. And here, instead of having a single image plane, which is shifted, multifocal displays consist of a stack of image planes, which are additively combined, for example, with a beam splitter. And so essentially in multifocal displays, we divide the scene into discrete layers. And within the volume spanned by the layers of the multifocal display, users can focus freely. And as you might have guessed, there is an upper limit as to how far these layers can be spaced and still provide at least near correct focus cues. And this has been shown to be about 0.6 to 1 diopters. A diopter is basically the inverse of a meter. And the downside of multifocal displays is that in order to cover now a wide accommodation range, a large working volume, you need at least about 4 layers, which makes these multifocal displays relatively bulky. But the advantage over varifocal displays is that you do not rely on eye tracking. So next we have light-filled displays, and they support near-correct focus cues by emitting directional light, which means they essentially try to replicate the real world. And this can be realized with micro-lens arrays or a layer stack of transparent LCDs, for example. The difference between light-filled displays and multifocal displays is that while multifocal displays have additive image formation, where each layer essentially adds light, in light-filled displays, each layer modulates a common backlight. Also, an advantage is that the 0.6 diopter constraint has not been shown to be relevant for layered light-filled displays. The downside of light-filled displays is that their resolution is limited, and layered light-filled displays also have less brightness than multifocal displays. So finally, holographic displays are also actively researched, and their image quality gets better and better over time, especially with machine learning approaches and camera-in-the-loop training. However, full 3D holography is still, in terms of image quality, somewhat subpar compared to what you get with an LCD. Okay, so that brings me to dynamic multilayer mixed reality displays. And here, essentially, what we try to do is get rid of the downsides of the individual aforementioned concepts by combining the concepts of varifocal and multifocal displays. And that leads to improved contrast compared to the other displays, and we demonstrate this with evaluations of our display prototypes in our papers. And also, in dynamic multilayer mixed reality displays, we present novel real-time rendering and display algorithms. So all these concepts that I will introduce to you in the next slides, they work in real time. And finally, and that was also pretty important for us, is that this concept can be built in a variable form factor. So all the prototypes we try to build at least in a variable form factor. Okay, so the first paper that I want to introduce to you is a TVCG paper called Video See-Through Mixed Reality with Focus Cues, which we presented in 2022 at IEEE VR. And yeah, actually, I'm proud that we got the Best Journal Paper Award for this work. So quickly, here are my co-authors and their affiliations. And yeah, the major contribution of this work was to build the first video see-through head-mounted display, which provides focus cues and also solves the vergence-accommodation conflict. So up until this point in time, all the work for solving the vergence-accommodation conflict was basically on VR displays and optical see-through AR head-mounted displays. And to my knowledge, at least, we were basically the first to try to solve this conflict in video see-through systems. So this was basically the main contribution. We also used a data structure called mixed reality focal stacks, and we show in the paper novel algorithms for capturing focal stacks, rendering focal stacks, and also improvements to displaying focal stacks on the display layers. So what's the reason to use a dynamic multi-layer display, in this case, for a video see-through system. So a few slides ago, I talked about how varifocal displays rely on precise eye tracking. And this is even more true for video see-through systems, especially when we want to display the captured scene with accurate focus cues. So let me quickly demonstrate how an eye tracking error affects the perceived image in such a video see-through system. So in this example, let's assume the user focuses on this green butterfly here, but the eye tracker in a varifocal system thinks that the user focuses on this distance here, which is marked by this black dot. So we have certain eye tracking error. And what will happen now is that, first of all, the cameras capture the scene with the wrong focus distance, which leads to an already blurry representation of this butterfly. And then the display is also shifted to the wrong location as well, which further blurs out the object the user is looking at. And this is actually what we wanted to improve in video see-through displays with our dynamic multi-layer concept. So essentially, in our final design, we used the concept of a dynamic multi-layer display. And that means that instead of just a single screen, we use a stack of 2 screens, like in a multifocal display. And we shift the whole stack according to the measured focus distance, like in a varifocal display. So essentially, as I said before, we combine the principles of multifocal display and varifocal displays. And this concept is actually illustrated here. So the user focuses on this butterfly, and on the left, we can see how the volume spanned by the screen stack, which is shown in blue, is moved accordingly towards the user. And as you might recall, a few slides ago when I introduced our multifocal displays, I told you that within the volume spanned by the layers of the display, users can focus freely. And that means for our system design, as long as the real user focus distance is within the 2 layers of our multifocal display, we can still provide our focus cues. And that's why the dynamic multi-layer system design leads to tolerance to eye tracking errors. It also has additional benefits, like being able to support a large working volume in a variable form factor. And finally, instead of capturing a single image, the cameras in our system capture a whole focal stack in order to get representations of the scene with correct focus distance across the whole volume spanned by the 2 layers. Okay, so let me quickly give you an overview of how we realized this concept in a prototype. And for the screen stack, our system consists of 2 LCDs for each eye, which are optically combined by a beam splitter. And both screens have a different distance to the beam splitter, so the virtual image of one panel will appear closer to the user than the virtual image of the other panel. And furthermore, we included a pair of focus tunable lenses, which allow us to shift the virtual images of both screens by changing their focal power, essentially. Additionally, we use a binocular eye tracker to measure the vergence distance of the user, which we mounted below the lenses. And for recording the environment, the real scene, so to speak, we use 2 industrial cameras. And again, 2 focus tunable lenses to control the focus distance of the cameras. So that's our prototype. And now I quickly want to show you this prototype in action. So here on the right side, we can see our prototype and also the user. And in the TV, there is a real-time simulation of what the user currently perceives. So, and as the user is looking around, the augmented butterflies are flying across the scene. And eventually one butterfly notices the hand and comes closer. And as the user focuses on this butterfly, please note how the background naturally gets blurry. So the augmentations and the real scene blurs out in the same manner. And then the user focuses on the background and the butterfly, and also the hand blurs out. And again, focus to the butterfly. So this is essentially a demonstration of the system. Also, I quickly want to mention this. If you're interested in all the details of the paper, so for example, the algorithms we used, for example, we show a motion compensation algorithm or a depth of field rendering algorithm to drive this whole pipeline for the display. Please check out the paper. It's freely available on our team page. And I will also show a QR code in the end, which you can scan. And it's also available on IEEE Explorer. So this presentation really just scratches the surface of these works, essentially. And I also realized that I have to hurry up quite a bit. So let's quickly move to the next paper. And the next paper I want to show you is called Gaze Contingent Layered Optical See-Through Displays with a Confidence-Driven View Volume. And this is also a TVCG paper that we presented at ISMAR in 2024. So here again, quickly, my co-authors on this work and their affiliations. And for this work, the main contribution is to introduce the first display which dynamically adjusts the position and the working volume based on the eye tracking confidence. So this was the main contribution. So in contrast to the system that you've just seen before, which essentially has a static volume that shifted, this display now is able to adjust the volume dynamically based on the current eye tracking error or the estimation of the current eye tracking error, essentially. The other contributions in this work include, so we introduced an automatic multi-layer calibration routine that allows us to calibrate a multi-layer system automatically with a camera placed in front of the HMD. And we also show an approach to compensate the varifocal change in field of view. So essentially, when you shift a layer or when you change the distance of the layer to the lens, essentially, what happens is that the perceived field of view of this layer will also change. And this might be annoying to users. So what we did was we came up with the method on how to automatically compensate for this in software. And finally, in this paper, we also demonstrate a novel focal stack decomposition approach. So as I said before, this work builds upon the video see-through system that I just presented, that I just shown you, which was a hybrid of a multifocal display and a varifocal display. And it had a static display spacing, and that led to enhanced contrast. So we have all seen this now in the slides before. And now in this work, we introduce an adjustable display spacing. And this kind of leads to optimal contrast due to the eye tracking error correction. And optimal here means that for a given eye tracking error or eye tracking confidence, we provide the optimal volume in order to show the best possible contrast to the user. And also, instead of a multifocal display, this is now a hybrid of a light field display and a varifocal system. And finally, it's optical see-through augmented reality. So this video demonstrates a prototype that we built. So you can see the two LCD layers moving separately. This means basically that they changed the volume. It's also a mechanical setup now. So there are actuators that move the layers individually. And yeah, we also used some end stops in order to get absolute positions of the layers. Okay, so what's maybe most important is that what is the impact of using a dynamic volume instead of a static one? And this video here shows a through the lens recording, which demonstrates how the contrast improves when we can use an optimal volume size. So here on the left side, we can see the current volume spanned by the two layers in blue. You can also see the user and the augmented butterflies. And after a while, and I will tell you when this happens, the eye tracking estimate or the eye tracking confidence improves. And so we can make the volume smaller. And as a consequence, the contrast will increase. So now we have a large volume, and suddenly the contrast increased because the volume got smaller. I hope you noticed this. If not, of course, we can also shift the whole volume towards the back as in the previous paper. If you did not notice this because of the fast-moving butterfly, here is a quick comparison between the static volume and the dynamic volume. And this just means that on the right side, we have a smaller volume due to the higher confidence in eye tracking. And hopefully you can see how the contrast of the butterfly and also the contrast of the text above the tablet improves. All right, so one other contribution that I quickly mentioned in the beginning of this paper is that we introduced the so-called magnification compensation approach, which is essentially an automatic calibration routine that's carried out once. for the whole system. And that allows us to compensate the change in field of view of the varifocal layer shifting. And we do this in software. So you can see this the impact of this approach here. So on the left side, you can see what happens when the layer is moved and it's not compensated. Oh, I have to start the video. And on the left side, you can essentially see how the field of view changes. And you can see this kind of pulsing motion as a result. And on the right side, you can see the same thing with the magnification compensation enabled. So hopefully you can see how the pulsing motion is now severely reduced, although the layer is still shifted in the same way as on the left side. Okay, so this was our second paper, and our final paper that I want to present to you is called Off-Axis Layered Display Hybrid Direct View Near-Eye Mixed Reality with Focus Cues, which is quite a mouthful. This is also a TVCG paper, and we presented this in 2023 at IEEE VR. So again, quickly my co-authors on this work and their affiliations. And in this paper, we kind of took a slightly different approach than in the other two papers. So here we want to essentially merge the capabilities of direct view displays, such as TVs or monitors, with HMDs. So here, essentially, the user wears an HMD and looks at the direct view display, as is illustrated here on the right side. And if you think about it, this essentially leads to a layered display with two layers, where the direct view display is the first layer and the HMD kind of creates the second layer. So we still have this two-layer setup here. And this slide demonstrates how this works. So here you can see a 3D direct view display. This is a passive TV and the user who wears an HMD. And this is essentially also a dynamic multi-layer system, because here the users themselves can control the working volume of the whole system simply by changing the distance to the TV. But of course, the question now is, what benefit does such a system have over a conventional 3D TV? So in this slide here, you can see what the perceived image when looking at a normal 3D monitor looks like when focusing to the front. And here on the top right, you can see the focus plane of the user. And you can see that the whole scene gets blurry, because we essentially have the same problem here with the single image plane as demonstrated in the beginning of this presentation. So essentially, as the focus plane moves towards the user, the whole thingy blurs out. And now you can see the same thing with our system, with the off-axis system. And you can see that hopefully the bird is in focus as the user focuses or wants to focus to the bird, and the background is blurred out, which essentially means that we can use the system to provide near correct focus cues. So here are some applications of the system. So for example, we can use it for gaming with focus cues, playing racing games, for example. Also, and I will demonstrate this later, we can use it for multi-user interaction with a single 3D TV. We can also use it for CAD modeling with focus cues, which I really like, because if you think about it, if you like model a machine and the machine really pops out of your screen and you can focus on the individual elements of the machine, yeah, that's quite cool. And finally, we can use it for interaction or exploration of a cave, also with focus cues. Right. So additionally, what we show in this work is the support of monoscopic direct view displays. So let's say the user does not own a 3D monitor or TV. How can the user still experience the same layered system with focus cues with a monoscopic direct view display? And we demonstrate how this is possible. Under one constraint, the user needs to have an optical see-through HMD with occlusion capability. And an HMD with occlusion capability is essentially a device which is also capable of blocking elements of the real world. And while these systems are not yet commercially available, at least mostly, however, a lot of research exists in this direction of occlusion capable HMDs. And such displays let you block the real world essentially on a per pixel basis. And we can essentially use this functionality to replace the stereoscopic direct view display with a monoscopic direct view display. So essentially, in this situation, the image formation process is TV times the occlusion LCD plus the content shown on the HMD. So that essentially means the occlusion LCD is able to block light coming or to modulate light coming from the TV. And what we do now, what we need to do now is to essentially show both the left and right view on the TV simultaneously, and then selectively block the correct view for each eye with the LCD in order to achieve stereo separation. And I will demonstrate how this pans out in the next slide. For now, I just wanted to quickly tell you that this also enables multi-user interactions. So if you think about it, if you have a single user, you essentially, for each eye, you need to block one view. However, if you have, for example, two users, all you need to do now is for each user block 3 views. So essentially the view meant for the other eye and the 2 views of the other user. This is how different users are able to view, for example, an individual user interface on a common shared TV. Okay, so as I promised before, here is a result showing how the system is capable of blocking a view. On the left side, you can see what is shown on each display. So on the top, you can see the pattern shown on the TV, the stationary pattern, which consists of both the left and the right view. Then in the center, you can see what's shown on the occluder, the occlusion LCD. And on the bottom left, you can see the augmentation or the virtual content shown on the HMD. And in the center image, you can see what the perceived image of the user looks like without the occluder. And you can see that if you would not have this occlusion capability, we would suffer from severe ghosting artifacts, essentially. But on the right side here, you can see that with the occluder, we can successfully block the other view, which is meant for the other eye. And thus, we can achieve stereo content without having a stereoscopic TV. All right, so quickly to conclude this talk, I've shown you 3 types of dynamic multilayer mixed reality displays, and each display has a varying degree of layer spacing adjustment. So the video see-through HMD has essentially a static spacing. Then the off-axis system that I've just shown you, which is a hybrid between a direct view display and a single layer optical see-through HMD. In this system, the user controls the distance between the 2 layers. And finally, in the optical see-through HMD, with an adjustable layer spacing, it automatically adjusts the volume depending on the eye tracking confidence. So these systems solve the vergence accommodation conflict. They have improved contrast compared to other displays, and also they work in real time in a variable form factor. So finally, let me talk about what needs to be done in order to kind of commercialize these systems. So first of all, we need to improve the form factor and also the ergonomics. And that means that we need to reduce the overall size, reduce the weight, work on the mechanics. So ideally remove all the mechanical movement from the system. And essentially, we want to realize this concept in a form factor like this. And actually, in my opinion, most of these points listed here are doable when you keep in mind that we built these prototypes from off-the-shelf components. But other aspects, such as the optics, are more difficult to get right. So first, let me quickly talk about the varifocal mechanism. In order to get rid of the mechanical movement, it's necessary to use varifocal optics, such as in the first prototype that I've shown. However, the field of view of this prototype was quite limited due to the small aperture of the liquid lens. So conventional lenses have a diameter of about 4 to 5 centimeters, whereas the focused tunable lens that we used only had an aperture of 1 centimeter, and this severely restricts the field of view. The problem is that if you want to make the aperture larger, it's not as trivial as you might think, because the liquid in the lens is actually affected by gravity, which kind of leads to optical coma, and this effect gets worse as the aperture increases. However, it's not entirely unsolvable, as we could, for example, create an optical stack with coma correcting elements in order to get rid of these kind of optical aberrations. Also, there are some limitations to the multi-layer display concept that need to be solved. First, regarding light field displays, the pixels of the front LCD, they act like small apertures which the light needs to pass through, and this leads to diffraction, which unfortunately has the effect that the real display appears blurry. And yeah, this effect gets worse as the resolution of the front LCD increases. But one solution to this problem would be to using LCOS displays instead of LCDs. So LCOS displays are reflective instead of transmissive. So the light of the real layer would not pass through the front layer, but instead it would be modulated and reflected. And second, for the multifocal displays, in order to improve the form factor and weight, we could realize the multifocal concept with a single high-speed physical screen and the focused tunable lens. And this would essentially allow us to create 2 layers only virtually by rapidly switching the focused tunable lens in sync with what is shown on the display. And alternatively, instead of using simple beam splitters as image combiners, we could use, for example, waveguides, which would also improve the form factor. So yeah, all in all, I think there is still a lot to do in order to create commercially viable solutions of this concept. But I also think that there is nothing, at least in my opinion, that I would say is impossible to do. Okay, so with that, I want to conclude my talk and thank you again for your participation. Again, so this QR code brings you to the webpage of our lab. And yeah, I'm happy to answer any questions you might have. Thank you.
Excellent, excellent talk. As I said, I was so excited to see your presentation at ISMAR and then to have you here today, because it's so highly relevant, as we know that the ecosystem of augmented reality users is frustrated, not just by vergence accommodation, but because we're not really getting the hardware that we one day would like to have and be able to use every day, all day long.
Yes.
And overcoming these problems is essential to getting that right. And so we need to continue working on it. And thank you for the excellent presentation.
Thank you.
So one of the things that I thought was interesting towards the beginning of your presentation, you showed past work, what inspired you before you started. And you showed 8 different research projects. Had any of them approached commercialization, or had there been prior attempts? I understand that you probably didn't, but were you aware of any commercial devices that attempted
yes,
commercial?
So there were some attempts. I gotta say though that I did not try them out, but I'm at least aware of them. So for example, there is the Magic Leap 1, which instead of having just one focus plane, I think it has 2 focus planes. And so I think what they do is they have an eye tracker built in, and I think they use the eye tracking to switch between the 2 planes. So that means if the eye tracker detects, all right, the user is focusing on a kind of near object, the focus plane switches from the far plane to the near plane. I think
so it's not tunable. It's not tunable, and it's not adjustable to the degree that your prototypes are, but it meets it part way. It still gets us part way to the problem.
Exactly. And the fact that they are doing with waveguides is even cooler, because I think their waveguides, they have actually 6 layers, because you need per layer, I think you need 3 colors. And at least from what I recall, they have a patent on that. It's just what I can see being a problem is the eye tracking. So, for example, also with varifocal displays, you have this eye tracker in there, and there is this method of determining the vergence distance of the user by intersecting the eye gaze with the depth map. But let's say you have a kind of a complex scene with a lot of depth discontinuities, a lot of fine structures in the near vicinity, and the eye tracker has a certain error, right? So it might be that the user actually focuses towards the back, but the eye tracker thinks the user is focusing at, I don't know, 30 centimeters, for example.
Right.
And I think then switching the focus planes might make everything worse. So, and this is this problem what we wanted to address with the dynamic multi-layer system, to not have a worse experience actually in this kind of concept, to try to solve the vergence accommodation conflict, but actually they might make it a bit worse. But again,
yeah. In fact, one of the questions that came across from the audience was, how do you deal with eye dominance? Because here you're talking, you know this problem, so I can see from your face that you're going to answer that. But also, when you wear corrective lenses, there might be, how does it accommodate those? How does it meet the needs of people who wear corrective lenses like me?
Yes, that's a really good question. Actually, this question comes up a lot. So, so speaking for myself, I don't have corrective lenses, so I might not be that familiar with this issue. But of course, you also want to support people who have corrective lenses. But I feel like, and this is always the answer that I give to this question, I feel like these systems, as soon as the eye tracking is able to correctly determine, or at least approximately determine, the vergence distance of the user, even with corrective lenses, these systems are perfect because they are essentially, they serve as an additional corrective lens. So a focus tunable lens can change the focus as you basically want it to, right? So we did not do any user studies, but if you ask about further directions, we definitely want to conduct user studies, especially with people who wear corrective lenses, because it's such an exciting field. And I think that these prototypes really play into this kind of
Okay. So, you also, it's so of today's time that we do data processing with at least machine learning or other AI techniques. Do you use any of those techniques currently in your system?
That's a good question. Yes. So we do not use machine learning techniques, but there are certain machine learning techniques out there, especially for light field reconstruction and layer pattern generation from a focal stack. So let's say you have a multifocal display, you have as your data source a focal stack, and for example, with our video see-through system, we actually capture a focal stack. You need to transform this focal stack onto this layer pattern. So you have just, say, 2 displays, but you're capturing a dense focal stack. You need some process of converting the focal stack onto the layer patterns. And for this, machine learning approaches exist. We also tested them, and we know that these approaches in our related work, because they are really cool. For example, one is deep focus, also from Meta Reality Labs, that has produced really nice results. In the end, to be honest, why we didn't use it, because we had a contribution already working, and for a research paper to simply use another system, it's not that interesting than presenting your own approach. And
original.
Didn't
yes,
use focus in our system.
I totally understand. And in fact, this is, it's a question also of where do you put the processing. It's clear that there is a lot of processing requirements in your system, and that requires a bigger chip, or it requires more energy. So you're depleting your battery in this process. If you can offload any of that, put it into an AI dedicated chip, then it can make your system more efficient, I think. I mean,
Yes.
you're the expert, but so about power and battery consumption. How far are you from making? You didn't mention it as one of the obstacles that needs to
Yes.
be overcome, but for commercial quality displays, you have to have them be quite power efficient.
Yes, that is totally. I totally agree, and you're right. I didn't mention these power requirements because it was also not the focus of our research prototypes. All of the prototypes that I've shown you are tethered, and they require a huge GPU to work, of course. So this would be maybe also a next direction in terms of, as you said, putting separate processes, separate stages of the pipeline onto separate chips, thereby decreasing the power requirements.
Right. Now, you spoke about the light field displays being part of your next generation, or it's part of your current project. Is it an important part? How do you view the evolution of light field in your project, or in displays in general? In optics, yeah.
That's an interesting question. So the choice of using the light field display was mainly, I would say, to demonstrate the dynamic layer multi-layer concept with a multiplicative layered system as well. So we had the multifocal system, which was additive. And then we thought, okay, we have this concept now, which consists of a varifocal kind of system and a layered system. And now, why shouldn't we also show it with the light field display, like a multiplicative layered system? So of course, these layered light field displays have really nice benefits, such as supporting proper occlusions, for example. But they also have problems like limited resolution due to the diffraction or limited brightness, for example.
They're working on all that.
Yes. Yes. So maybe finally, I would not consider light field displays as being superior to these additive systems. They're just a different way to realize the concept of dynamic multilayer displays. And actually in our paper, we dive into the individual advantages and disadvantages of multiplicative versus additive.
Okay. Well, so I know the question on everybody's mind, which is, when can I buy this? When will it become commercial? Now, of course, that's not your responsibility, is it, Christoph? You're doing the innovation, you're doing the research, and someone else has to commercialize it. But so can you tell us who's going to commercialize these technologies sooner?
It's so difficult to predict. I can also tell you that a lot of big companies are working on commercializing that, of course. I have no idea how close they are.
They're going to make you rich because you hold the patent?
I'm not sure about that. I can say that I hope it will be commercially available as soon as possible. Let's put it like that.
So does everybody else.
Yeah, exactly. Yes.
It's very, very interesting. Okay, well, I think that wraps it up for today. I think we should just look to you for many future developments and innovations. Good luck in your research, and thank you very much for sharing with us today.
Thank you for having me. Thank you so much. It was a pleasure.
Bye now.